In the previous video, I showed you a simulation of how the Doppler shift for waves is produced. Now we're going to talk about its specific applications with light. Well, Doppler radar, airplane radar, submarine radar, anything with radar uses the Doppler effect because light can be produced and can bounce off of objects and come back, especially if we're using something like radio light, and that can be used to detect motion towards or away from the observer. Even radar guns used by police officers, state troopers for example, utilize the Doppler shift of light to detect the speed of moving cars. And this only works if the cars are moving towards or away from the person with the radar gun, but it's also a very accurate way of determining speed. Today, I'll tell you about how you can do that. So remember that the Doppler effect is this change in the wavelength due to the relative motion between the source and the observer. And so if something's giving off light and it's moving towards or away from you, then you'll experience a Doppler shift. So here's a star, it's giving off light, it's not moving with respect to the observer, and so the wavelengths it gives off will be the same detected by the observer as they are emitted by the source. But if a star is moving away, let's say the same star is moving away from the observer, then the waves that are detected by the observer are going to have an apparently longer wavelength. This is called a redshift. And if a star is moving towards the observer will detect apparently shorter wavelengths. So just to summarize, moving away, longer wavelengths, and this is called a redshift because red light has longer wavelengths than blue light, and so for Doppler shift of light, we just call it a redshift. Conversely, if we're talking about a star or an object that's giving off light moving towards the observer, the waves that are detected by the observer will have shorter wavelengths. Shorter wavelengths correspond to bluer light, and so we call this a blue shift. And remember, this has to happen along a line of sight. And so if the star is moving towards or away from the observer, we'll be able to detect a Doppler shift. But if the star is moving side to side or tangential with respect to the observer, it's not moving towards or away, so we won't detect any Doppler shift here. So side to side or perpendicular motion, no Doppler shift. So how do we do this in astronomy? Well, we look at the star's photographic spectrum, and that will allow us to discern any Doppler shift that's involved. So let's take a star that's not moving with respect to the observer, that is, those of us here on Earth, and here is the star's photographic spectrum. We can see that it has absorption lines, and those absorption lines have a specific spacing between them. If the star is moving away, then those absorption lines will actually be shifted to different wavelengths. Because the star is moving away, then that means the wavelengths that the observer detects are going to be longer wavelengths. And so all of the absorption lines in this spectrum should be shifted to longer wavelengths. And that's to redder wavelengths, and so they should be shifted to the right. Notice that the relative spacing between the lines is the same. So it's still the same pattern of lines, they've just been shifted over to the right. If we're talking about a star that's moving towards the observer, then the wavelengths detected by the observer are going to be shorter wavelengths, and so the relative spacing between the lines will be the same in the photographic spectrum, but they'll be shifted to shorter wavelengths, so to the left. And that's how we do this in astronomy. The reason is because you can't actually see a color change in the star due to the Doppler effect. And that's because objects in space are really not moving fast enough relative to the speed of the wave, and in this case that's the speed of light, to make a big difference in the actual color of the star. So just because a star looks red doesn't mean that it's red shifted. We have to look at the actual absorption lines in the photographic spectrum to tell. If we want to look at this more quantitatively, then we can use the Doppler shift mathematical relationship to do so. Here's how it works. The wavelength of the particular spectral line in a photographic spectrum is represented by the Greek letter lambda. And if we're looking at the rest wavelength of that absorption line, where it would be if there was no motion between the source and the observer, we call that lambda sub 0, and that's the rest wavelength. Delta lambda is the change in the wavelength from the original rest wavelength to where it's actually observed by the person who is detecting the waves. V is the velocity of the source, or the relative velocity between the source and the observer, and c is the speed of the wave, and in this case it's the speed of light. Notice that the bigger the change in lambda, the bigger the change in the wavelength between the source and the rest wavelength, the bigger the velocity. Or vice versa. Really what that means is the bigger the relative speed, the bigger the change in the wavelength will be. So the size of a Doppler shift depends only on the relative velocity between the source and the observer. If we look back at this mathematical relationship, you'll see that there's no d for distance here. It doesn't matter how far away the object is. The only thing that matters is the relative velocity between the source and the observer. And so distance is not a factor. So the distance between the source and the observer is not going to affect the size of the Doppler shift. So the larger the relative velocity, the larger the Doppler shift. So what can we learn by looking at the starlight that we receive? Well, we can get the star's temperature, we've already learned, by looking at the peak wavelength of the spectral curve. If we want to know what a star is made of, its chemical composition, the dips in the spectral curve or the lines in the absorption spectrum will tell us that. That is, looking at the particular dips and their pattern in those spectra. And then finally, we can look at the Doppler shift to discern the star's motion. These are very powerful ways of learning about things far out there in space just by collecting the light and by analyzing it, looking at the spectra.